Okay. So this is the last class, and we'll be looking at modeling of lumped components on transmission line. These are the list of references, important information. And in the last class, we covered the calculation of S parameters, and we looked at the code as well. And in this class, we will see individually the modeling of resistors in series or parallel, capacitors in series or parallel, inductors in series or parallel with the transmission line. So any questions from the previous class on modeling of S parameters? So where we had the two-port network and we introduced a source and a source resistance or at either ports and calculated the auxiliary parameters, the A and B, the power wave for the power waves, and then we calculated the S parameters from the A and B. So and we looked at these results and we had looked at the code as well. And as an assignment, I had shown you how to calculate S11 and S21, and I had given us as assignment to calculate S12 and S22, and try to model a low pass filter and high pass filter and see their S parameters. Any questions on this? I'll pause over here just in case if you have questions. Otherwise, we'll continue with the modeling of lumped components. I hope my screen is visible. Can anybody please confirm if the screen is visible and I'm audible? Still not sure. Okay, so this we got a confirmation that the screen is visible and the audio is there. So I guess no questions. So we'll do the modeling of the lumped components, and the material that we'll cover in this class is borrowed from this particular paper by Thomas P. Montoya. He's a professor in South Dakota School of Mines, I guess, in Department of Electrical Communication Engineering or some electrical engineering. And the paper name is Modeling Transmission Line Circuit Elements in FDTD method. And this particular paper is in Wiley's Microwave and Optical Technology Letters. So it's a very good paper. And we'll start. The paper starts with modeling of simple 1D transmission lines, and so I'm going over this again because this particular paper uses some different scripts to denote some parameters. So we all remember the telegraphers equations, right? So these couple of equations, they are the telegraphers equations, and this is the model of the unit cell, and this particular unit cell is for a lossless transmission line. Now, L and C are the distributed capacitance and inductance per unit length, and delta Z is the length of the incremental section. Now, for this particular transmission line, we have already written the update equations, and I'm showing you this again because in this particular paper, we are using cursive I and cursive V to denote the voltage and current and the discretized voltage and current when we have taken finite differences and performed all the mathematics or the operations. And these are the update equations, and where these coefficients will again be used as alpha, so beta and gamma in the code. So I'm sorry, this should be just a minus symbol, not an equal to. This is minus, and this will probably become gamma, and this thing will become beta when we are writing the codes. So these are the update equations. You can see after once we have discretized I into the present and the past terms, and then rearranging, we get the latest term of I in terms of the past value of the I at the same node and the past values of voltages at the neighboring nodes. Similarly, once we have discretized voltage over here, we will get voltage, the latest value of voltage in terms of the past value of voltage at the same node, and current at the neighboring nodes from the past values. So so these are the discretized telegraphers equations as shown in the paper. And then the characteristics impedance is given as Z, and the propagation velocity is Vp. And using these, we have just written LNC terms in terms of the characteristics impedance and the propagation velocity. And the notation used over here is in cursive V. Now, for parallel inductor or transmission line, here we have included the inductor in parallel with the transmission line. So, if you recall from the previous figure, we have the inductor, there is distributed inductor over here, the distributed capacitance over here, and then there is a lumped inductor added in parallel with the distributed capacitance. So, we modified our unit cell, and in the unit cell we are having this inductor over here whose value is LP. Now, once we have this inductor over here, we again perform the KVL and KCL, and you can see the KVL expression remains the same because we only have voltage drop across this inductor over here. So voltage over here minus the voltage drop across the inductor equals the voltage the second node. But for the Kirchhoff's current law, at this particular node, now we have two branches, and the third branch is this one. So current flowing through this branch minus the current which went through the inductor, lumped inductor, minus the current which went through the distributed capacitor, and minus the current in the final branch. So this is the expression we get from KCL. And what we have done is we have written the current through the inductor, through the lumped inductor as ILP. So ILP is the term over here, and now we need to calculate ILP. And to do that, we do it this way. So the current through the inductor is given as 1 upon LP, integral of the voltage across the inductor plus the initial value of current which was flowing through the inductor. So if you remember the current's expression, the relationship between current and voltage in an inductor, so using that we have written this expression. So by using KVL and KCL, we get these two expressions, and for the current, we are using this expression over here. And then using these three expressions, like performing finite differences, we get the update equations. So for the first equation, so the first equation is unchanged. So again, we have the update equation for the current. Now the second equation has a new term ILP, which is again added over here, and this particular ILP has to be updated, and for that we will use the third expression, and we have approximated this integration as summation over here. So ILP plus the previous all values of ILP plus this integral value. So this LP remains same, this dt becomes a delta t over here, and we have the voltage value at every instant. So this integration is now approximated as a summation, and we have the two update equations over here. So this is how we get the update equations for a lumped inductor on the transmission line. And then once we have these three update equations, if you must remember we had the code looking like this, where we had the first for loop for updating the voltage. Let me just use in over here. So this particular loop is for voltage, and this loop is for current. This loop is for current, and for all other cases, this is the update equation for the voltage. But at the location where we have introduced the inductor, so we will modify that particular node where the inductor is introduced. And for example, if this is your simulation space, and this is your z direction, and at z equals to lk, if this is the location of the inductor at the so we are introducing inductor over here. So at this particular node, the update equation for voltage and current has to be modified. And since there was no change in the update equation for current, so this particular loop will remain as it is. But for current, we will modify this particular node, and instead of using the regular voltage update equation, where we will use the modified update equations. So now the modified update equation says that voltage is in terms of the previous value of voltage, the current values which was already there, and then there is a new term for ILP. So included this ILP term over here, and we now need to update ILP. So ILP is now updated based on the second equation that we got. So ILP is equals to ILP plus delta T by LP, which is dt by LP, and multiplied by the voltage value. So this is the only change that we have to do in the code. And once we have done that, we will obtain the we get the final FDTD code, and then we can simulate this. Let me, okay, how do I remove this pointer? You will see. So we have this Gaussian pulse excitation from the source. This particular pulse will move towards the load, and it will encounter the at this particular position. We had the inductor on the transmission line. So due to which there was some reflection, and some of the wave propagated. So this is how it will happen. You can see due to the inductor, the propagating wave uh, experienced some changes, and hence we have simulated the inductor successfully. So any questions on this? Okay, so this was pretty much straightforward, and in the similar fashion, we will go through all the lumped components. So this was inductor in parallel with the transmission line. Similarly, the next case would be inductor in series with transmission line. So now we have an inductor in series with transmission line, and the inductor value is Ls. So so in this particular case is very simple, because what we do is we just take the equivalent value for the lumped inductor and the distributed inductor. Since the distributed inductor in this particular unit cell is if you multiply it with delta z, it becomes the it becomes its lumped equivalent, and we just have to take its equivalent value of this inductor, that is this summation, and applying KVL and KCL. The only change we see is over here. So we have the voltage at the first node minus the voltage at the last node, and the voltage drop across the inductor, which is this particular value. And the summation of the two inductance values, one of them is multiplied by delta Z, and the current flowing through the inductor. So this is and only this expression has some changes. The second telegrapher's equation does not see any change. So this remains same. And then we again use the finite differences on these two and get the update equations. So we get the update equation for current over here, and the only change again we are seeing over here is in this ZC dash term, where ZC dash is calculated with the characteristic impedance plus the this particular value which has come due to inclusion of this lumped inductor over here. So Ls into Vp by delta Z, which is then added to the characteristic impedance. So this Z dash is the change over here. The update equation for voltage remains same. So we have got the update equation for current. We've got the update equation for voltage. Now we'll use them in the code. So in this case, since the update equation for voltage remains same, so this loop is not changed. Now the only change we have seen was in the update equation for current, and since again we are including inductor at some position Lk, so we'll just wait for we'll instead of using the regular update equation for current, we'll use the new update equation, and in that we just modify this term over here, this Z1D, which is calculated according to the previous expression that we have seen. So this Z1D can be calculated before the loop even starts. So before the for loop starts for the FDTD, before that we will just calculate the value of ZD according to the characteristics impedance and the rest of the values. So we can do that. So that's all the changes we need to do. So and the voltage expression was not changed, so no change in the loop for the voltage. The current expression changed, so we'll just instead of using the regular update equations, we'll use the modified update equation for the current at the position of the inductor, and that's it. So once we have done that, we can simulate our code and we'll get the uh, effect on the wave propagating through the transmission line. When it encounters a series inductor, the wave will see some reflection and stuff. So you can see, so there is some reflection again, and due to the inductor which is located at some point over here. So we have covered parallel inductor and series inductor. I'll pause again over here just in case if you have any questions. Maybe I'll move to the previous slide. You can look at the equations and let me know if you have any questions. So before we move to the capacitance cases for the lumped capacitors, one important announcement. Since this is the last class, after this class, I'll share the feedback link. So it is very important that you fill up the feedback form so that I get the record of students who have been attending this particular course, and the course attendees who have filled up the feedback form will only get the participation certificate. So make sure you fill up the course feedback form, because without that I won't be able to provide you with the certificates. Okay, so we'll move to the modeling of capacitors. So now for the parallel capacitor case, we will include a capacitor in parallel with the transmission line, and what we have done is we have included this capacitor in parallel. This capacitor is now in parallel with the distributed capacitor over here. So what we can do is we can just take the equivalent of this capacitor and modify, and then so that KVL and KCL equation will perform, and the modifications will be seen over here. So so the lumped capacitor CP is now in parallel with the distributed capacitor, and this is the only place which is modified. So the update equation for current will be for the update equation for voltage will be modified with, and the update equation for current remains same. So from the first equation, we find the update equation, which then this is again same. And the second from the second telegrapher's equation, we get the second update equation for the voltage. And over here, the characteristics impedance gets modified. So this ZC double dash is calculated in this fashion. So what we can will do is, once we have declared the position of the capacitor and the value of the capacitance Cp, will immediately calculate the value of Zc double dash, because we know the values of Zc, Vp, and delta Z, and now Cp as well. So we'll calculate Zc double dash and then use that in the update equations. So since the voltage update equation was modified, so this particular for loop gets modified, and at the location of where the capacitor has been included. So if the capacitor is located at Ck, so this is our simulation space, and we have the capacitor at location Ck. So at Ck, what we'll do is we'll use the modified update equations, where we have Z1d, which is calculated as shown in the previous slide, and for all other points we'll use the regular update equation. And since the current update equations were not changed, so this particular loop remains the same. So the this is how we modify the update equations and the for loop for the code, as seen over here for these two particular cases. And after doing that, we can just simulate our code, and this is how the results will look like. So you can see we'll have some lumped capacitor over here, and the wave will experience some reflection, and there will be some transmitted wave. So we had some reflected wave as well because of the capacitor, and some of it was transmitted. So this result is obtained from the FDTD simulation. I'll share the codes with you at the end of the class. You can try running them by yourself and try to vary the value of capacitance, inductance, and resistance, and see what happens. And also, I'll share the paper by TP Montoya, and in that paper, the results have been compared with analytical solutions as well. So what you can do is try to write the code for the analytical simulation as well, and compare the results again. And any doubts from the modeling of uh, parallel capacitor? Okay, so then we'll move to modeling of series capacitor. I can't see my pointer. Okay, let me just use the list. So now we have included a capacitor in series with a transmission line. So and the voltage drop across this capacitor is given by VCS. Now on this particular modified unit cell, where we have this lumped capacitor CS, we'll perform KVL and KCL. So the KVL expression changes. So the voltage at the last node minus the initial voltage, and the voltage drop across the two across the two elements, the lumped capacitor and the distributed inductor, is shown written over here. So this is the voltage drop across the inductor. This is the voltage drop across the capacitor. And now using KCL, we get the second telegrapher's equation. And since there is no change in the shunt elements, this particular expression remains the same. And now to calculate voltage drop across the capacitor, we use this particular expression, where the voltage across the capacitor is calculated by 1 upon Cs, an integral of the current passing through the capacitor, plus the initial voltage which was present across the capacitor plates. So this is the expression from the KVL and KCL. So it's very simple. We have just modified the unit cell previously as well. And we have added inductor in series and parallel and capacitor in series and parallel. And upon adding that, we just perform KVL and KCL and try to write down the finite difference equations. So these are the telegraphers equations along with the way the expression how it will calculate the voltage across the capacitor. And once we have got these, we'll just perform by using the central difference technique. We'll write down the FDTD update equations. So this is the expression for current, which is modified because now we have a new voltage term occurring over here. So this we have VCS over here, and the update equation for voltage remains same, so no change over here. And to calculate VCS, we will use the third expression that we have, which is the approximation of the integration by using summation. So we are just using summation by adding the delta voltage value at each iteration to the final voltage value across the capacitor. So we have got these three expressions. Now we'll use them and modify our code. So voltage expression does is not changed. So this particular loop remains the same. Now, these two are the voltage expressions for the boundary conditions for where we have the source resistance and the load resistance and the excitation. And the current update equation for the current was modified. So if the capacitor is located at the CK location, so we modify the update equation at that particular node. So we had the first expression where we had VCS. So VCS is added over here, and to calculate VCS, we're writing this in MATLAB. Uh, so this where we have this delta TS dt divided by VCS multiplied with current value, and we're just adding it. So the integration was approximated as summation over here, and this particular expression was modified by adding VCS. So after doing that, we can run our FDTD code, and we'll see that the propagating wave experiences some reflection where we have the capacitor. So at this particular location, we have the capacitor in series. To see the wave experiences some uh, reflection and transmission. So that's all for series in series capacitor. So we have looked at series inductor, series parallel inductor, series capacitor, and parallel capacitor. So any doubts up till now? So we just have series register and parallel register left with us, and that will be all for this particular course. So before that, any questions from all the classes that we have done or what we have covered today? So we began the class with modeling of transmission lines. We looked at its lumped equivalent circuit. Uh, we looked at its lumped equivalent circuit. Then we had an introduction to CEM, and then finally we had then we started with the FDTD codes. It's very tough writing with the mouse pad. Um, so we started with the distributed transmission line. We looked at its lumped equivalent circuit, introduction to CEM. Then we wrote the FDTD codes. We then calculated the S parameters, and now we're looking at the lumped elements. Just a second. I hope I'm audible. And just check. Did I unmute myself? Yes. Okay. So we have looked at the series inductor, parallel inductor, series capacitor, and parallel capacitor. Now we'll look at the resistors as well. So this is the case for the parallel resistor, where we have included a resistance in parallel with the transmission line, which is RP over here. And then again we do the KVL and KCL on this particular circuit, and you can see the voltage. So the KVL expression remains the same because we just have only inductor doing a potential drop over here. And for the Kirchhoff's current law, we have now two branches over here. So the current in the first branch minus the current in the final branch minus the current through the capacitor minus the current through the resistor branch. And through this resistor, so this is the current through the resistors branch over here. And we can look at this particular term. So this particular voltage term is not in the form of derivative. So now we need, and since we are calculating voltages at different nodes, we need to find, we need to calculate, we need to approximate this particular value as well. And to approximate this value, what we do is we take the average of the nearby, we take the average of the nearby nodes. We so yeah, this looks all right. Are these the two same terms? Okay, there is some error in this thing. Just correct that. So this would be just the minus symbol over here. Yeah. So what we do is we take the voltage values at the neighboring nodes and average them so that we get the voltage value at this particular node. So that's all we need to do. So we have approximated this voltage value, and this particular on the voltage and this on the first Telegraphers equation does not does not have any changes. So the update equation is as it is for the current, for calculating current. And for the voltage, we have new terms over here. So if we take minor differences and simplify, we'll end up with something which looks like this. So don't be scared of the so many things in numerator and denominator. Just make sure you do your math properly and enter them correctly inside your MATLAB code. So we'll get these three, we'll get these two update equations, and this is how we have approximated the voltage value over here, and we'll introduce this into the update equations. So let me just change back to pen. Yeah. So the voltage update equation is modified, and this was the update equation, right? So make sure, like if you know the operators correctly, then you can skip so many brackets. To be very sure, I have included all the brackets so that there is not any mistake in calculating these coefficients. So this is just coefficient, just include them, multiply it with yeah, multiply it with the this voltage value over here, and then the rest of the coefficient with the differences in current over here. Yeah, so this entire thing and this entire thing is just one coefficient. Include that and write down the update equation. So the inductor has so the resistor has been included at the position RK. So this is, if this is your simulation space, you have this, you have your source over here, you have your load over here. We will include the register at location RK. If you have the register at location RK, we have modified the voltage update equation to this expression over here. And since the current update equation was not modified, so this remains the same. So we modified the two loops, and then we can run the code, and we'll see that we have some the traveling wave is affected by the resistor. Since we know the resistors just create losses, and there is impedance mismatch. So we'll have some reflection over here and some attenuation over here. So that's all for the series parallel resistor. And then similarly, we'll do the same treatment for series resistor. And so you can see we have included a series resistor over here, and then we'll perform KVL and KCL. And upon performing KVL, we have potential drop due to this resistor as well, which is included like this. And since we have this current term over here, we need to approximate this current term. So this is how we approximate the current term. We have taken average value of the current for the for the two different time steps. Sorry, for the two different locations, n plus half and n minus half. And this is how we approximate the current volt value over here. And only this particular expression is modified. This expression is remains same. So we have the final difference equation for voltage as similar to the regular update equation, and the update equation for current gets modified. Again, we have this huge coefficients, so we just have to write them correctly inside the FDTD code, and that's it. So the voltage expression is not modified, so this particular loop remains same. The current expression is gets modified. So again, we have included the resistor at location RK, and the at location RK we are using the modified update equation. So you can see this particular term is written over here and written over here, and the second this term is again written over here. And we have simplified this particular thing as gamma. So we have just labeled this thing as gamma, so we are writing gamma over here. So we modified the update equations in the MATLAB code, and then we can use these codes to simulate the series resistor. At this particular location, which is in the middle of the simulation space, we have included the resistor, and due to the resistor, there will have some reflection and attenuation. So you can see the amplitude of the wave was reduced, and we have some reflections due to the impedance mismatch. So that's all. So we have seen the modeling of the resistor, capacitor, and inductor, and we have seen the modeling of lossless transmission lines. Now you know how to model series inductor, parallel inductor, series capacitor, parallel capacitor, series resistor, and parallel resistor. What you can do is try to include the resistor over here, try to include a resistor over here, and then model the lossy transmission line. So this is an assignment. We have seen calculation of S11 and S21 when we have source at source at port 1. Now what you can do is have source at port 2 and calculate S22 and S12. And once you are done with that, what you can do is model the CRLS transmission line where you have inductor and capacitor like this, and inductor and capacitor like this. So this is the unit cell for CRLS transmission line. You already have seen how we modify the KVL and KCL update equations in all the different cases. So this is the CRLS transmission line, and if you include resistor over here as well, you'll end up with lossy CRLS transmission line. So this is left as a do-it-yourself assignment, and this is actually a very good project if you're a master's student. Try doing this. So that's all from my side, and this is the end of this particular course. I'll take any questions that you have in general about the course, or if you have any feedback that you want to share with me. And soon I'll share the feedback form as well, where you can score different aspects of this particular course. And make sure you fill up the form regardless whether you want to fill up the form or not, because if you want the certificate, you must fill up the feedback form.
Anand, I have a question. Could you hear me?
Yes.
First, again, it was a very nice course for us, and I'm very, really happy since I have seen you last 7, 8 years how you work in this microwave engineering. So, and, first, I would like to congratulate you. You have done a very good job. And then
Thank you so
the
much.
second thing I would like to ask, uh, very, very fundamental thing, at the last point of the load resistance in the very first code, we use real resistance RL and
Yes.
whatever ZL. So suppose we want to take some complex kind of thing. So how do we do?
Okay. Since we have gone through this all the material of this course, we have enough knowledge how to modify the unit cells. Now, to do this, there is a paper by there is another paper by Professor T.B. Montoya where he has shown how to include complex load and source resistances. So there's just one paper. It is a conference paper where he has shown if we have a complex impedance at the source, for example, series RLC or a parallel RLC with the source, or series RLC or parallel RLC with the load. How to include that? If you follow that paper, just search about. Uh, I'll share the slides. You'll see the name of the professor as well. Just search his name and along with FDTD, another keyword, you'll get that paper and you can try modeling that. So he has written all the update equations. You just need to put that inside the code and model. You can run this.
Okay, then
So
it's
there's a
fine. Yeah.
yeah. So there's a paper exactly on the question that you asked. And since you have covered all this thing, you will be able to grasp what is written in that paper.
Yeah. Okay. I have. And I also do the kind of a cascade thing that you taught also. I have done that, but I don't know the exact solution. So I don't think is it right or wrong. I done the cascade thing and all those steps, but I
Okay.
don't know what would be.
So the best way would be to write since you have done the cascading of different impedances, right? So what you can do is
Yeah, yeah,
find out you know the length of the transmission lines, and you know the impedance. What you can do is calculate the ABCD parameters for individual sections, multiply them and get the ABCD parameter of the entire network, and then calculate the S parameter for that network using a MATLAB code separately, and then verify the S
yeah,
parameter of the simulated FDTD code and the analytically done one that you did with the ABCD matrix. If both of them match,
yeah. This
it's
is
correct. So that is the way
okay.
with
So
I had like verified some of my codes.
okay, yeah. The last thing that I put only in my notebook that where I am missing to actually calculate something. In some lecture you taught us that you need to compare with some analytical solution also, and for that
Yes,
analytical results, you say कि
yes,
आप लोग कर लेना because this is not my part of the lecture. So I
yes,
just try to calculate that analytical value because there is only one unknown, that is V not plus. We can write in our equation in that term, uh, potential Vz in terms of V naught plus blah blah blah. Hello,
yeah.
and using
So
initial. So
yes,
I'm
yes,
I'm wondering how we can calculate because we have an initial condition in time domain and we have an expression in frequency domain. Is it?
yes,
We have initial condition in time domain. Whatever the condition we have, all are in the time domain. Either t is equal to 0, we have some initial condition, either some boundary condition for time variance also. Huh?
yes,
Variant. We don't have the actually initial condition for frequency domain. So
yeah,
for that, I'm not able to actually. I tried very hard 2 3 hours on how to calculate V1, and I get V1, but I'm not very satisfied with myself. Yeah, this is the right way to do.
Okay, I'll tell
Because
you a
somewhere
simpler
it
way,
comes like,
which
yeah,
I'll
yeah,
tell you a simpler way to so we know how to calculate S parameters from the FDTD model, right? We have got
yeah,
the we know how to calculate the S parameters. Now I'll just briefly write the write down how I do it, which is much simpler than doing that much mathematical uh, work. Let me just get a pen. Okay, so what you need to do is you calculate the S parameters from your FDTD model. Okay,
yeah.
so whatever sorry, I'm writing very slow because I'm using the mouse pad from my laptop. So we calculate the S parameters from the FDTD model. Then and to verify whether our model is working correctly, we have got S parameters from here. The next thing you do is, for example, you're trying to simulate some structure which looks like this. You have some transmission line with, for example, this could be some 50 ohm stuff. This could be maybe 100 ohm. Okay, and then again this could be some 70 ohm. So this is the cascading thing which we are talking about, right? So this is how it will
Yeah.
look like. So in FDTD we know how to
Mm.
simulate this because we have done that in the class. Now
Yeah, yeah,
what you can do is, you know the length, you know the impedance, so you can calculate the ABCD matrix of this particular section,
yeah,
which is written in terms of something as tan beta L, some coefficient into tan beta L, or sin beta L, cos beta L. So it's there in the textbooks and the POSA. So it will be a 2 cross 2 matrix for each of the section. So for each section, we'll write down the ABCD parameters. Okay, so we write down the ABCD parameters for each section. Now, since they are ABCD parameters, what we can do is we can multiply all of them. So once we multiply all of them, we'll get the ABCD parameter of the entire network. Don't care about any boundary conditions. We just write down the ABCD parameters for each individual section, multiply them, get the ABCD parameter for the whole network. So once you have got the ABCD parameter of the whole network, there is a formula in POSAR which directly tells you if there is this particular, you have the ABCD parameters of the network, you can directly calculate the S parameters from that. So you'll get the S parameters from the for the entire network from the ABCD parameters. So this has to be done by hand, and to ease the calculation, you can write on the MATLAB code. You just enter the matrices value and multiply them easily in MATLAB, and just convert directly. And MATLAB also has functions which can calculate from S parameter to ABCD. You just have to write S to ABCD, something like that is the function. So you'll get the S parameters for this particular thing. And this has to be done for each frequency. So since the ABCD parameters are frequency dependent, so for each frequency, you can do this. You can enter the entire code into in a for loop and run this for different frequencies, store the S parameter values, and then plot that. So once you can plot the S parameters from this particular function, and from the FDTD simulations, you know how to get the S parameters. You can match them. So this is exactly how I do it, and it is very simple if you have a circuit which looks like this, where there are cascaded transmission lines. Did you follow? Any questions on this
yeah.
method?
I'm listening. No, no, no. It's fine. But I'm wondering how to, because it's a tough thing. It's not easy thing, because what we do normally, we can not used to do the calculation of this initial value condition and try to find v, exact what is V in transmission line. So many problems are dealing with this, only reflections and some Smith chart, whatever. We are not very much interested in what the exact equation of what voltage with Z and
Yeah.
omega.
Yes. So
So the first time, once you said that कि आप ये कर लेना, then I'll just try. Then I think, oh, we don't have any boundary condition in terms of omega. So first I need to convert this in time domain. Then I got some kind of a delta function somewhere, and then again it's very tough to actually. It's somehow I'll just do it because I know the answer, so I just get answer. But I'm not very satisfied. Is that the right way to do? That's why I
Yeah,
asked.
I think you're going through a much more like tough analytical calculation you're trying to do.
Yeah, yeah.
Don't
Yes,
try
yes.
to calculate the voltages and currents now. Everything is being done in the FDTD, and you know how to obtain S parameter for a device. So instead of calculating the voltage and current expressions, what we can do is we can just match the S parameters, which is much easy to calculate analytically as well. By calculating the ABCD parameters. We don't have to calculate
Yeah,
any
yeah.
voltage or current in this particular case.
Yeah,
So
yeah.
what I can
But
do is
other things
maybe
are fine.
I'll share I'll try writing a code as soon as I find time, and I'll share the analytical code as well and the FDTD code for the same thing to show that how we get these parameters for the two things. So when you'll see the code, you'll actually understand that this is very simple how to verify the S using S parameters. You don't have to calculate the expression for voltages.
Okay, okay,
So
fine.
it looks it seems tough, and because maybe I'm not explaining this very clearly, but it's rather very simple, and you don't actually have to care about the voltages and current expressions. They won't be involved. Calculating S parameters from ABCD parameters is pretty much straightforward if you know the impedance and the length values.
Yeah, it's okay. Everything, other things are very good. So I'm very impressed with you this lecture and previous also.
Yeah,
Both
thank you
was
so much.
both were good.
To solve your doubt, I'll definitely try to share the code which like the way which I'm trying to explain. Maybe this is I'm not able to convey it correct the best way. So I'll try to do that. So this problem is solved.
Okay, okay. Thank you.
Thank you so much. Any other questions? Any follow-up questions on this? Anybody else as well? Before we end this particular lecture and this particular course. Okay, so if there are no further questions,
Anand,
I'll yes.
I also like to say something. Could you manage to do one more course about the basic thing on some other computational technique like MOM and FEM? So for some basic fundamental problems, so that we can understand. Yeah, this is a simple problem, and using FEM because using FDTD we solve some problem. Similarly, you taught us FEM and MOM also, but we are still not able to solve any problem. We know the
Yeah,
basics, we know the each and everything. So I we just need to know how. Suppose we know FEM and we have some problem using FEM, we solve this. Using MM, we solve this. Then we I think it would be beneficiary for us, and I think so many undergraduates and PG students, they want to come in this field.
so since I don't work on these methods, I know very little on about these, like very limited amount of examples that I know, and hence I'm not very confident if if I have enough knowledge to like conduct a course with. So I'll try if like as if I get time.
हाँ वही मैं ट्राई के लिए ही कह रहा हूँ क्योंकि you are very good actually teacher also to make us understand each and every very बारीक जिसको बोलते हैं. So ये थोड़ा सा सही होगा. Otherwise other things are nice.
Sure,
And one more thing,
definitely. Yes.
Anand. One more thing. It's still I'm working on FDTD since last 5 years, but I'm still not able to I have not have a mastery to calculate S parameters of antennas and filters. So could it be possible to have any kind of like a patch antenna and other thing stuffs, and we can able to calculate? Does it possible
Using FDTD, yes, but it will be
using
very
FDT?
expensive. It will be very computationally expensive if you write a 3D codes to do that. But if you I'll recommend resorting to existing solvers because they are more efficient. But using FDTD, you can definitely. So there are some examples on MathWorks website which you can directly download and run. So there is example for a filter. There is example for a patch antenna as well. But it takes very long to simulate those things. But it is possible. I'll recommend, since you already have like working knowledge of FDTD, you have done written codes as well. So just try Googling. You will get the codes on the MathWorks website, and you can run that. So those codes are actually also present in a thesis by a fellow named as Bharata Yajman from Texas Tech University. So I'll write that in chat.
Okay.
Bharata Yajman from Texas Tech University. So his MTech thesis actually, his MTech thesis uh, is actually on FDTD simulations for patch antennas and filters for 2D, 3D cases with lumped elements on them. So what you can do is go through his thesis. It's a very short thesis with which has explained a lot of things, and the same codes are also has been written by somebody, not Bharat Yajman, but somebody else, and they have uploaded on the MathWorks website. Download them, run them, and what you can do is then modify the code for your needs.
Yeah, fine. Okay. Thank you.
Okay, then. Thanks, Ankit, for for appreciating me so many times. Anybody else, any questions?
Hi, Anand. Actually, I have a question. While I was doing this course some years back, so you see, this 1D equations, the meshing is fine, but when we have a, let's say, a 3D structure, like a irregular 3D structure, like we have a CAD geometry of that one. So how you will do the meshing of that in FDTD?
So this problem becomes very complex in case of 3D and if it is irregular. So the simplest way is to use the 1-0 technique. That is, we fill dielectric. Is there is I hear some echo.
So just hold on a minute.
Okay. So
Yes.
what you can do is fill if a particular cell is completely full with the dielectric, we assign the dielectric value. If it is free space, we assign the free space value. And if it is
Okay.
partially filled, we decide by ourselves whether we should assign it 0 or 1. Now the another technique is to use some there are some expressions like there are papers which gives you expression. So if it is half filled with dielectric, what we do is we take an average of the two dielectric values which are in that particular space. So the cube has, for example, it is half filled with epsilon 4 and
Okay.
epsilon 6, so we take an average of 4 and 6 and fill that value over there. And people have given different expressions for calculating how much is it full and how much value should we assign. So that is some sort of grading thing is done if it is
Uh,
if a particular cube is half full. So did you follow?
yes. I understand. Actually, as far as I understand, that FEM has some meshing algorithms, right?
Yes,
Like,
FEM has machine.
yeah, FEM has some meshing algorithms, and we just applied those meshing algorithms, and we can make the mesh. So,
Yes.
so similar to that, FDTD does that have the equivalent meshing algorithms?
Um.
Because I couldn't find
y-
when I was doing that.
Yeah, so I have not encountered with any standard meshing algorithms for FDTD, since FDTD is actually a meshless technique, so we don't actually mesh it. So we put the entire divide the entire simulation space
Mm.
into cubes and then assign the permittivity
Yes,
values
exactly.
for so that so people you so most FDTD codes are actually home written, is you can say. So
Yes,
scholars and
yes.
researchers, they write their own codes and use their own way of filling those dielectric inside the matrices.
Okay.
So far I have not also encountered any technique, and there aren't many industry solvers which are based on FDTD. So there is CST which is based on FIT, and I am not sure how does CST does the meshing part. So I think it also approximates
Mm.
into the cubes as well, and
Okay.
as I've seen inside the simulation space, but I am not very sure, like I'm
Okay.
not confident. how it does.
Yes. One term I heard while researching about this, that was something called voxel. Something you voxelify and 3D geometry. So maybe I can look into that. You can also look into that.
Yeah.
There is something called voxel geometry. So they use that one. But
Okay.
I couldn't find more into that. But that term I still remember. So
Yeah, thanks for
that's
telling,
about it.
because
Huh.
I have not researched much on this, but I'll write this in the chat for myself as well,
Yes.
and
Voxel
everybody
geometry.
can.
Plus,
So I'll also look into this voxel geometry thing, and maybe if I come up with something interesting, I'll share it in the WhatsApp group that we already have.
Yes, yes.
And if you
Okay.
do get something, do share.
Yes, yes. Okay. Thank you.
Any more questions regarding the course, or any feedback that you want to give it to me directly?
Anand, one last thing पूछना नहीं चाह रहा था. So, hello.
Yes, yes, Ankit.
This stability have you taught us? Have you done a numerical dispersion for this case?
Uh, no, I have not done much studies on numerical dispersion for this thing, because I believe I was following the Courant limit, and things looked fine and
What?
stable. So I did not do much for this thing.
नहीं, this actually जो हमने पहले में हमारा जो आता था डेल्टा टी कुरेंट लिमिट के लिए कम इट कम्स फ्रॉम न्यूमेरिकल डिस्पर्शन. वहीं
Yes.
से आता था डेल्टा टी इज लाइक दिस. सो यहाँ जो डेल्टा टी का एक्सप्रेशन आया था, इज इट कम फ्रॉम द अब इज कहीं से ड्राइव करके आया, या आइदर वी जस्ट कंसीडर द कन्वेंशनल केस कि वनडी के लिए
So
ऐसा होना चाहिए.
So the codes which I'm sharing, in that, I have written the expression from the one which I had used in PML. So this code is kind of legacy code for me. I've been making changes to that. So it still follows the Courant limit, but it has some n powers cube stuff written over there. So it's actually derived from what was the condition for PML if it was in 3D, but it still satisfies the Courant limit. So that's what the expression, if you're talking about, in the code which I've shared.
नहीं, ठीक ठीक है, बस यही पूछना था. The other things are very good. And once again, I would like to thank you. Because I'm working on this. I've never seen so many people around me. Only you and some like one, two, three people more out of 100 microwave researchers. So I still feel कि कोई है जो कर रहा है. चलो कुछ कुछ बोल तो रहे.
Thank you. Okay, then we'll end today's class here. If there are no further questions, you can again email me or message me on the group. Um, so I'll end the class here. I'll share the slides and the recordings in some time, and the codes as well. Thanks everyone for staying throughout this course and joining this course. And do fill the feedback form.